So now in this type we will discuss about Miller's theorem. Miller's theorem is only applicable when there is a bridging capacitor like this CGD. So this is the formula for Z1 and Z2. We need to find K. For K we need to do the midband analysis. For midband analysis you will just open the capacitors. Okay, I will just open the capacitors here. You will just see that how this works. This is your R6 and here it is your R1. Here it is your R1 and R6. This is your R6. When you open them, so they disappear. You are left with only this part. So I am drawing it. So when you draw this, it would be like something this. This is your RL, and here you also have to take the output voltage. This is your output voltage. I am not writing that. This is GM/VGS. So this is your V6. This is your V6. This is your R6. This is R1. This is these resistor parallel combination. This is GM/VGS, and you have to take output here. So now I will apply KCL at this node. So when you apply KCL at this node, so you will see that both are leaving the, you will see that this is the factor GM/VGS plus V naught GM/VGS plus V naught divided by it is equal to 0. So you will see that V naught upon VGS, you will get V naught upon VGS, you will get minus GM/RL phi. So this is your factor. So you can denote this as, this is your value for K. So your K is minus GM/RL this. So now you are left with C1 and C2. C1 would be like, okay, C1 is multiply this CGD this bridging capacitor with 1 minus K. Okay, I have written it for you. So you have to just incorporate the value of K here. So I will just incorporate the value of K here. You have minus sign, you will get C. This is a C1 and C2 is equal to CGD. Again you have to write this bridging capacitor with, and here comes 1 minus 1 divided by K. So just put the value of K. You will notice that this becomes a plus sign, and here it is GM RL pi. So you have found out C1 C2, so job will get easy. After that we will just place them in our model. So our model was like this: a voltage source with resistor with R1 here, and here you can see it was CGS. Basically we have broken down that CGD. This was your GMVGS. Here you have that RL pi with and a capacitor. These all are grounded. I will replace them by this notation. This is your voltage source. And this is also a ground. See, now this was your V sig, this was your R sig, this was your R1, and the capacitor would be CGS plus C1. This capacitor is C2, this is RL prime, and this is your GMVGS. So we have reduced the circuit in this form. So now again you will find omega 1 and omega 2, that what are the values of omega 1 and omega 2. So now you will just see out that what are their values. For omega P1 and omega P2 you will simply use P. So now tau is equal to RC. This will be the formula you will be using. So if you applied KCL here at this node, you will notice that it will be GMVGS plus, here it is V naught upon RL, and using properties of Laplace theorem plus V naught upon 1 over SC2 is equal to 0. So now you have got that equation. If you will solve it for V naught upon VGS, you will simply get 1 upon 1 divided by SC2 and RL phi. You will just solve it, just use basic mathematical properties and you will get this value. For that, this side of tau, you can see that these are in parallel. These are in parallel. So tau would be, here it is your omega pole 1. You have to write it like, because V naught upon VGS is this. This is the V naught by VGS. It is not your V naught upon VGS, but it is your omega P2. This side is for omega P2. When you will solve it for V naught upon VGS, you are simply getting minus Gm divided by S C2 RL plus 1. So you will find tau, you will neglect this and you will only write this part, main concern part. So omega P2 will be this. If you will solve this portion, you will see that R1 and R6 are in parallel. So you will see that tau 1 here, I have just tau 1 here is R6 in parallel with R1 and just multiplied with this, it is CGS plus C1. So omega pole 1 would be simply 1 divided by tau. So 1 divided by tau would be similar to this here, omega pole 1. This is for omega P1 and omega P2. So that's how Miller theorem is so much effective technique. Just revise it. High frequency, we created a high frequency common source amplifier. We short circuited the capacitors. We created a small signal pi model, grounded the source and replace these 3 capacitors with this RL phi. Then we used a Miller theorem. Z1 is equal to 0 over 1 minus k, Z2 is equal to 0 over 1 minus 1 upon k. We did mid-band analysis. We opened the capacitors and then in this step we found out V naught by VGS, which is k. So main part here is that we have to find k. Then you will simply use C1 and C2. C1 is just that bridging capacitor, or multiply it with 1 minus k, and k value is this, and here simply C2 was for C2, just use CGD 1 minus 1 upon k, just incorporate value of k and you will get these figures. So now again you will see that bridging capacitor is removed using Miller effects. You added C1 here and C2 in parallel in here. When capacitors are in parallel, they are added. See, the C1 was here, but it is added because in capacitor parallels add. Then you will find tau for both areas. I found it for second area. Used KCL, we found out V naught upon VGS, and omega P2 was 1 upon SC2 RL. And for tau 1, simply this is in parallel with this capacitor portion, and omega P1 is equal to 1 divided by tau 1. So this was for two poles, P1 for and pole P2.